reduction. In today's lecture, we will discuss about dissolving metal reduction. As I have told you, the reduction can be defined as the reaction where a species at a higher oxidation state is converted into a species of lower oxidation state, or in a reactant, if we add hydrogen to the molecule to give us the product, that means any reaction which is performed by gain of electrons or addition of hydrogen is called as reduction of that molecule. And because metals, they can easily give us electrons to become a positively charged atoms. That means they have high reduction potential and they can act as reducing agents, and that is why most of the reducing agents, they are based on metals. And metal hydride reductions, they are probably the most widely used organic reactions which are used for these types of transformations. And as I have told you that there are these are the three types of hydride complexes which are very prominent for these types of metal hydride reductions. And all lectures on all these lithium aluminum hydride, alkoxy aluminate reagents, and borohydride based complexes we have already done. And today's lecture we will discuss how dissolving metal reduction takes place. As you know that alkali metals, they can very easily transfer an electron, and that electron can be transferred to the organic molecules, and reduction can take place by delivery of proton from the solvent. So thereby the transfer of electron followed by transfer of proton can lead to the formation of reduction products. So when an electron is transferred to an organic molecule, that means metal will be transformed into a cation, and a radical anion of the organic part will be formed, and that radical anion will abstract proton either from water, alcohol, or ammonia, which are being used as proton donors, and they are sorbents for these types of reactions. And if we don't use water, alcohol, or ammonia, we can also use primary or secondary amines as sources of proton transfer to the radical anion. Then depending upon the ability of the metal to reduce organic compound, uh, this will depend upon how frequently or how efficiently the metal can deliver the electrons. So that means the reduction potential of the metal is very important for determining that how fast or how efficient the reduction reactions with metals will be there. So as we know that standard reduction potential of lithium is highest, followed by potassium and then by sodium. That means lithium will be the most efficient metal for dissolving metal reduction, followed by potassium and sodium. So such type of reactions where metals, they are used for reduction of organic molecules in presence of protic solvents, polar protic solvents, they are called as dissolving metal reduction. Now we will discuss reduction of different types of function groups one by one. First is reduction of alkenes and alkynes. So when metal reduction is used for the reduction of carbonyl compounds, carbon nitrogen, and carbon nitrogen double bond and carbon nitrogen triple bond, these can take place very efficiently because of the polarization of the molecules. Whereas in case of alkenes, the dissolving metal reduction is efficient for those alkenes where these carbon-carbon double bonds they are conjugated to a phenyl ring, or they are conjugated to another double bond or an aromatic compound, aromatic ring. So then these types of alkenes they will undergo reduction. For example, if you see this alkene, you can see that this carbon-carbon double bond is conjugated to this benzene ring, whereas this is an isolated carbon-carbon double bond. So when dissolving metal reduction is done in presence of lithium metal in ammonia using liquid ammonia as solvent in ether, then this is a selective reduction of the carbon-carbon double bond which is conjugated to the aromatic ring, and this isolated carbon-carbon double bond is not affected. So that means here in this type of reaction we can say that the selective reduction of only those carbon-carbon double bonds will take place where the double bond is conjugated to either another double bond or a phenyl ring or an aromatic ring. Similarly, in case of alkynes, the alkynes they are transformed into transalkenes, and you can say that partial reduction of alkynes take place and no further reduction of the alkenes to alkanes will take place. So this is again a selective and advantageous method. So when sodium metal is used in liquid ammonia, then this type of carbon-carbon double bond compound is reduced to transalkene as the product. And the reduction reaction is a very selective reduction reaction. You can see that these silane group or ether group, methoxy group, they are not affected by the reduction of these types of substrates. Then is reduction of conjugated dienes. As you have seen in case of alkenes and alkynes, that the dissolving metal reduction is a selective reduction. So when we have conjugated dienes and isolated carbon-carbon double bond. So the dissolving metal reduction mainly produces the alkenes where reduction of this conjugated ion will take place, and isolated carbon-carbon double bond is not affected by it. So again in such cases these types of dissolving metal reductions they are selective in nature, and the product formed can either be 1,4 addition or 1,2 addition reaction product, but the major product formed is 1,4 by the 1,4 addition of to give us alkenes as the product. So for example in this particular case in the this reaction is used in the synthesis of trichodine, which is a conjugated diene on treatment with dissolving metal reduction in sodium in liquid ammonia. So we get 65% of 1,4 reduction product as the major product, whereas 1,2 reduction product will take place over here, and the ratio of 1,4 to 1,2 reduction product is 85 to 15%. So you can see that the major product formed is a 1,4 reduction product. Now similarly carbonyl compounds they can also undergo dissolving metal reduction, and as I have told you that the first step is the metal provides us the metal cation and an electron, and that electron which is generated from the metal interacts with the substrate, that is the carbonyl compound, and we can have the isomeric intermediate formation in the form of radical anion. So either this type of radical anion is formed, which is in equilibrium with this type of radical anion. So this radical anion will take up proton from the solvent, and we will get this type of radical, hydroxy radical, and this hydroxy radical will take up another electron from the metal, and this type of hydroxy carbanion is formed, and this hydroxyl carbanion then will take up another proton from the solvent, and we will get alcohols as the product. So for example, in case of acetone, we will get isopropanol as the product if the reaction takes place in this manner. And second thing is that this type of radical anion can dimerize to give us this type of dicarbanion, and this will take up two protons from the solvent, and we will get glycols as the product. Similarly, this type of free radical form can also dimerize to give us glycols as the product. So this is how carbonyl compounds, they can be converted into either alcohols or glycols depending upon the reaction conditions. So the reduction of carbonyl compound is not very selective because different types of products they are formed during the dissolving metal reduction. Then some more examples of reduction of carbonyl compounds which are of importance in case of synthesis of some very important biologically active compounds. For example, if we are having this type of tricyclic ketone, so you can see we are having a ketone group as well as a hydroxy group, and in these types of reactions the dissolving matter reduction shows a good diastereoselectivity, and the reduction of the tricyclic ketones take place from the exophase of the molecule, and we will get the product where hydroxyl group will be in the equatorial position. So ketone will be reduced to alcohol as the product. Then another example is in case of reduction of steroidal ketones. For example, in this alpha beta unsaturated steroidal ketone, when this is reacted under these conditions, undergo dissolving metal reduction, and we will get deoxycholic acid as the product ultimately after the few more steps after the formation of this compound. And you can see that in case of alpha beta unsaturated ketones, the only carbon carbon double bond is reduced, and carbonyl functional group is not reduced. So this is again a very selective reaction for the synthesis of ketones from alpha beta unsaturated ketones. Then a few more examples of production of alkynes. As I told you that alkynes, they are converted into transalkenes. So in this cis alkyne, when this is reacted under these conditions, this is transformed into a transalkene of this type to give us partial reduction of alkynes to alkenes. So this is also very selective reduction reaction, and the general mechanism for reduction of alkynes is that in the first step an electron from the metal ion from the metal is added to the carbon-carbon triple bond, and we will get this type of radical anion. and this radical anion will take up one proton at this place, and we will get this type of radical ion as the intermediate. Then this radical ion will take up one more electron from the metal atom, and this will become an radical this will get converted into an anion, and this anion will take up another proton from the solvent molecule to get converted into transalkenes as the product. So this is how the final formation of transalkenes takes place as the product, because protons, they are added one by one from the one side, in the first place from this side, in the second place from this side. So that is why we are getting the trans product. Then depending upon the type of metal used, we can get different types of product. So for example, if we are doing partial reduction with the diphenyl acetylene, and we are using lithium metal in THF at minus 78 degrees centigrade, then both the lithium metal cations, they will add to the carbon-carbon triple bond from the same side of the molecule, and we will get a dilithio cis dilithiolkene as the intermediate. And when deuterated methanol is used as the solvent, these are replaced by deuterium. So we will get deuterated cis alkenes as the product when we are using lithium metal as the dissolving for dissolving metal friction. But if we are using sodium metal, then addition of the sodium takes place in a trans fashion to the carbon-carbon triple bond to give us disodio diphenyl ethene as the intermediate. And when this is reacted with methanol, the sodium ions, they are replaced by protons, and we will get this type of trans alkene as the product. And here the disadvantage of the reaction is that in addition to the partial reduction product, we will get also a saturated alkane, or full reduction of the carbon-carbon triple bond to a saturated product will also be there. Then in some cases, when we use dissolving metal reduction, the cleavage of the hetero bond takes place. So for example, in case of O-benzyl or N-benzyl derivative, the cleavage of carbon oxygen or carbon nitrogen bond takes place. At such type of cleavage reactions, these are called as hydrogenolysis. So hydrogenolysis is basically not a reduction reaction, but this is a reductive cleavage of these types of derivatives. So when sodium metal in liquid ammonia is treated with such type of derivatives, then cleavage of O-benzyl or N-benzyl group will take place. So mechanism of the reaction, for example, in case of O-benzyl molecules, when this is reacted with sodium metal, the electrons they will add to this substrate, and we will get radical anion of this type. And then this radical anion will undergo cleavage at the carbon oxygen bond at this place, and we will get this type of carbonyl, and this type of radical is formed. Then both this radical will take up H radical from the solvent and will be converted into this type of aromatic compound, and this will be transformed into an alcohol. So this is how we will get different types of products by hydrogenolysis of O-benzyl or N-benzyl derivatives. So in case of O-benzyl derivative, we will get alcohols, whereas in case of N-benzyl group, we will get amines as the second. Then some examples in natural products in case of hydrogenolysis. For example, in the synthesis of alloperine, this type of heterocyclic compound having N-benzyl group attached to it. So here the cleavage of this N-benzyl group will take place. At this place, and carbon nitrogen bond will be cleaved, and we will get toluene and the secondary amine as the product when we use lithium metal as the for dissolving metal reduction in diethyl in using ethylene diamine as the solvent. Similarly, in the second example, in this case you can see that this is having acetate groups at different functional groups in addition to this benzylic ether moiety present in the substrate. And here also carbon oxygen bond at this place will be cleaved, and we will get the corresponding methylene groups as the product. And here the metal used is lithium metal for dissolving metal reduction, and in addition the hydrolysis of these reduction of these ester moieties at these places will also take place, and these will be converted into the corresponding alcohols. Whereas these ether moiety present at the aromatic ring is not affected by the dissolving metal reduction. So these are some of the lectures which have already been uploaded for metal hydride or dissolving metal reduction. For example, bits reduction. The whole lecture is available on YouTube. Then Clemmensen reduction, zinc amalgam HCl is used over here as the catalyst. The lecture is available with this link, whereas some non-metallic reductions like Wolff-Kishner reduction has also been uploaded on the YouTube. So you can go through these lectures also for different types of reduction reactions. So these are the references which have been used for preparing this lecture. Thank you very much.